All right. Okay. So the first one, I believe everyone can hear me. The first one is just to quickly show us how I inserted the screw, right? So just a quick one. We are done with this session. So just when you head to your design, you could just turn off the top and some of these features. So there's something called insert, right? So earlier on, we used to use the insert manufacturing parts or MasterCard. And then somewhere along the line, last year, Fusion decided to add this to us, which is the insert fasteners. Someone saying something?
We're not seeing your screen, it's blank. Well, we can't, they will have to put that in.
How about now? How about now?
I can see your screen, Mr. Funny.
Okay. All right, Mr. Felix, are we good?
It's still not showing up for us. I have to log out. Yeah, you can go ahead now. Thank you. Now.
Okay. How about my audio?
Yes, it's working. Yeah, go ahead.
All right. Thank you so much. So just a quick one. Just wanted to show us how we inserted the screw. All right. So I said earlier on we used to use the insert master car and insert master manufacturing parts to do play around with some of those accessories. Last year, Fusion came up with the insert fastener concept, which actually made it very very easy for us to bring in screws. And the good part of it is that it's automatically ties the joint for us as well. So it gives us a lot of flexibility. So you don't need to waste your time on making things like that or trying to model stuff like that. So a quick one, we just head on to we are working with the ASCII metric standard, and of course we are looking for a screw. So I'll just select a screw. Let me pull this a little down. So a round head screw. So I'll be using the cross recessed pan head machine screw. So upon selecting this, now it gives us the dialog box where we can select the size. But when you see your nominal size, this is where you can now say, okay, since you're working with M6, so you pick up your M6, and then the length 18 mm. And you could also look around with the material and all of that, but we just leave this on default for now, and the finishing as well. You could also include your part numbering so that when creating your bill of material, those things will be included. So I haven't selected all of this. All I need to do is just to move in. This house effective. This is very simple. Just move in. Make sure that Fusion is able to. That's why we are using holes, right? When creating stuff like that, Because if you're using something like maybe an extrude cut to achieve this, it could be troublesome sometimes. So since we use hole and then the hole is also a standard hole, a threaded hole. So bringing this our M6 here, Fusion will quickly pick what is happening there. So can you see what happened? Just select. And the beauty of it is that everywhere on this board that has that same size is an automatic selection. If you notice, I just selected one, but we'll have it everywhere. So if I click on OK, and that's how easy it is. I've been able to put on 4 screws with just one step, right? So I just wanted to show us that because it's quite what's important. Sometimes we could waste a whole lot of time, trying to get things like this on. If you notice, if I zoom in, you will see this. This means that there is also a joint assigned as well. So it also knows that it's not just staying there, but it's actually gripped to the system. So it makes life way easier for you. And you can also maybe if you made a mistake, head on to here, right click, and then edit the fasteners. So I will stop sharing this Fusion. I just wanted to show us this. I think that was the last thing remaining. Right? So I believe we got that. Okay. So now the next thing I will be sharing is the section proper that we have for the second session. Right. Our design for additive manufacturing, which is commonly called DFAM or known as DFAM, and generative design. Now, we actually added or combined both of them. They're actually two different things altogether, but they have where they have a kind of unity, or where there is there is some form of how do we call it now, a link between the both of them. You understand? So, and since we have been working with, so we're talking about design, product design, printing, 3D printing, and all of that. So we just have the two, these two combined. But like Mr. Felix earlier pointed out, these are bosses on their own, like things that you can go into for a while and you're not done, getting everything around it. But just have to merge it so that the class could also get interesting, right? So I believe we could all see my screen. Please, Mr. Toli, you could confirm.
Yes, go ahead.
Yeah, please go ahead. Thank you.
All right. So we've already met myself, so I don't need to reintroduce myself. Okay, so we just move straight to additive manufacturing. We're talking about design for additive manufacturing. So before heading down to design for additive, it will be important that we actually even understand what this additive is all about, right? That will make common sense. So when we talk about additive manufacturing, and sometimes you hear people also say 3D printing. There is 3D printing is like a common name for also referring to additive manufacturing. So there are two things that stand out about it. The first one is that the terminology additive manufacturing is an official industry standard term for the application of all the application of technology. So the question will be, what technology are we talking about? And so that leads us to looking into, we're talking about the process of joining materials to make objects from a 3D or model data. So this is more like your digital data now, right? And usually this is done usually by layer, having the materials joined layer upon layer, as opposed to subtractive. So in subtractive manufacturing, where you're looking at, you have a hole, like a stock, right? That's the right term. And then you excavate material, and the remainder is the product. In additive, the reverse is the case, right? You're putting in these raw materials to form something. You understand? But it's also not, there's actually formative, which is injection molding. That's what's different. All right. So the key things you should take away is that so there is this one, what they call joining of materials, layer upon layer, right? And so, some examples of this additive manufacturing, because I remember someone did ask, that was the session on Tuesday, if the the technology I talked about was, the FDM was the only technology, and I think the person also asked if the material PETG I mentioned was the only PETG and PLA tough was the only one, which I said no. Okay, so that leads us straight to this additive manufacturing we're talking about. What are the the types? I'll be a little bit snappy because of our time, so we'll just try and understand. But of course, there will be opportunity to ask questions. And if we cannot address all today, we'll still take it probably some other time. So that leads us to the major additive manufacturing technology. I call this major because there are still research in this direction that is still so there are still more newer ways of going about this 3D printing that probably is not yet in the mainstream. It's not widely adopted yet. You understand? So, but for the ones that are like very common, the ones that we are seeing all around us being put to use, are these ones you're seeing on your screen. So the chart above, what you have under what you say FFF, SLA, SLS, and so on and so forth, they are basically called what? Technologies. So that technology we saw up there, we were saying what technology are we talking about? So these are the fused filaments fabrication as FFF, or what? FDM. They mean the same thing, just that the one for the FDM was a term that was trademarked by the people called Stratasys. So when you hear FDM, you hear FFF, we are talking about what? The same thing. FDM will be fused. FDM will be fused deposit modeling, right? Okay, so the next one we have like the SLA and the SLS are also other technologies. And now under these technologies, we have what are called processes. So a process is tied or common to a particular technology. So you talk about material extrusion. Someone who is conversant with this like 3D printing will already know that okay, you're referring to FFF, for instance, right? Because how does FFF take place? There is what is called material extrusion. As simple as that, right? We have SLA, which is a technology. Now, how does it take place? There's something called what? Polymerization, right? Same thing we have for SLS and so on and so forth. So we already have them on our screen. I wouldn't want to really go into all of that, but you could notice something. There are some we call polymers and there are some we call metals. So this also answers the question that was asked, I think it was Tuesday as well. I will also have cases where we are looking at metal or 3D printing. You understand? You can see something called powder bed, right? So we have powder bed for polymers. Polymers are like plastics, thermosets, thermoplastic, and the rest of them, right? While the metals are, of course, you know your metals already. So these are the major additive manufacturing technologies that we have. But the one that is so common, where you just see people talk about 3D printer is mostly the FFF and the SLAs. Probably because of the use case, probably because of the costing, and other things around that. So I'll quickly move on to the next thing. So, as expected, is if we have a technology and we have a process, and then that means there's going to be probably a workflow, a manner in which we are going to follow in order to get to our destination, or we want to produce maybe a silicon mold, right? We want to produce a silicon mold. How do we go about it? You understand? So now that takes us to what we call the additive manufacturing processes. All right. So a typical additive manufacturing process involves what we have been doing since, I think, for the past, let's say, 2 days. After you've done your background work on product requirements and the rest of that, and you're now on the software to implement. Now, when you're done implementing, just like we have done some minutes ago, as you're done, you're getting your design out, right? That's the first one you're seeing there, producing a 3D file, right? Now, why we have 3D scanning, generative design, and all of that mentioned under it is because we can't obtain a 3D file in just one manner. There are many ways we can get it out, right? There are many ways we can get it out. There are even reasons why we need to follow those many ways, right? For instance, the 3D scanning you're seeing there can be used for what's reverse engineering. Understand, which is a topic for another day. The generative design you're seeing there is also another concept which we probably also get to touch today before we all go home. So the first one where you see parametric CAD modeling is what we have been doing since. Parameter is this, shell is this, extrude from this place to this place, this should be related to this. If this move, this should, all those were things we have been doing. We have been doing modeling in a parametric tool. You understand? So either way you are using, the important thing is produce a 3D file. And of course, the file will also have a format, right? When you see .dox, you know what it means. When you see .mp3, .mp4, you know what it means, right? So these are how that's how it applies to even the fusion we are working on. If you see .f3d or maybe you see something or maybe .ipt, you know, maybe a part file for a particular related to a particular software, maybe Inventor. And okay, this one F3D, oh, this is a file coming from Fusion. So all those things which enable that communication for maybe this software or that software to be able to understand the file. You understand? So just like that, we also have it in the the 3D printing aspect, where the file you are outputting from your design, whether you scanned or you did a generative design, will have to be in a particular format. And the most common is what we call STL format, right? We have OBJ, we have 3DP, we also have 3MF, which is not included here. You understand? And then this format, which we are talking about, will also be a determinant to the kind of data that file is carrying, right? So if you're having maybe a file where you want to capture both the coloration and all those other things with the file, you probably want to export your 3D model file in maybe a format of maybe 3MF, right? And then if you just want maybe something that just carries just the information on the nodes and the lines, the vertex, and all of that, are those things that come together to form that shape which you're seeing. Maybe you just want to go with maybe the XTL file format, but whatever file format you're going with has to be understood by a software called a slicer, because the slicer, what it will do, will interpret the design you have exported to understand, okay, there's a hole here, there's this here, there's that there, there's a round, that's a fillet, maybe a chamfer. You understand? And then you will now use that slider to optimize your design for for printing. That's to obtain a physical print.
Just hold on. Just hold on. Just hold on. Just hold on. I think the power went off. Is it at the back here? We lost power here, so just hold on. Okay, we are back. Just go ahead. The mic is muted. We are back. Can you hear
All
me?
right. Yes, I can hear you.
Okay, thank you.
All right, thank you so much. We will see how we will do, because I think we want to go more beyond 2:30, so Tolu will help me with the time keeping. So I'll just see how much we can cover today. All right. So we were on the processes, like a typical process. There could be some, little variations depending on the very specific kind of maybe approach you're using. But this is basically the processes that are involved. So you have your data, like I said, you move on to exporting that data, or the data will be exported in a particular format that will be understood by a third-party software, which we call the slicer. So you see all those, you could see on my screen, FTAP, Simplified 3D, Slicer, Cura, and the one I use up to the Flash print. Those are all our things that we use towards optimize our the file we got from the card, the category, right? And then we now use the slider to optimize this design that we have done, so that it would be manufactured and then give us the desired result. So it could be, oh, I want it to be firm, I want it to be maybe brittle in nature, and all of those things. So that's where now in the slicer, you now have to do those control. What kind of material are we using? You put in your material, maybe PLA or PETG. What's the wall thickness? What's it called? The infill density you want to use, and all of those things, right? At the end of the day, you will now have your print coming out in a specific what, having a specific kind of what, probably output, right? So I'll just quickly move on to the third stage, which is okay now. So you've gotten the file and you've manipulated the file, and now you want to print, right? So that will be the next thing. You now head on to your printer, as you now perform the 3D printing operation itself now. So you are now like maybe the operator. You send your file to the printer, and then do your setups, and then get the printing going on. So after that process takes place, the next thing, you have to get the print off the build plate. Yes, is specified, or is being emphasized, because it's actually very important. It's one thing to print, it's also another thing to get it off. It could seem like maybe just a little thing, but when you are dealing with maybe delicate materials, or materials that are what, large in size, you will now know that yes, truly, even getting it out from the bed is also something you need to take very seriously. So you get your material, you print, that's your final print now from your machine out of the build plate, and then finally you will now carry out an operation called post-processing. So it's a whole lot. You see them listed there. It could mean that you're trying to remove the support that made your printing a success. That's also post-processing. It could mean that you're trying to carry out maybe sanding or curing, right? You understand? Or maybe polishing, priming, painting. You're trying to coat with spray painting, and so on and so forth. So those are all post-processing. That's after you've gotten your print out of the machine. You're now trying to get it to have that maybe finished form or look, and so on and so forth. All right, so quickly just move on to the next slide. So what are you might ask. So if you know what the additive manufacturing is, and then the processes. So the question would be, what are the benefits? Why should we go for this? We have subtractive, and they have been there many years, another form. So why should I go for what's it called, the AM technology, when we have these other many technologies? Now the truth of the matter is, all other existing technologies are also useful and important. They have their use cases. They have when they are lots, when they are kings. As when you get to that particular domain, this is the one that can serve that purpose. You understand? So we are now looking at the part where 3D printing is also like a lot on its own. Not saying that other printing technologies are not maybe okay or important, right? Just want to clear that. So the first one of the major benefits of AM is that is quicker than the conventional manufacturing process, from concepts to prototype to final product. There's something we normally call rapid prototyping, right? So if you even notice, this word came into play, you understand, especially when we had, not as if it has not existed, but it became very frequently used when we are talking about things like maybe 3D printing and the rest of them, because it's almost like you just get your design data out, you just plug it in somewhere, something produces it, gives you the result. You're like, oh, maybe I don't like the way this place is, maybe we should increase the depth of the what boss. You go back to the software, you do a little change, you fire it back to the machine, and then you get what, another output. So you could see that how fast that process of when you say testing your what idea, your product idea, to to actually know, oh yes, we've done our own work, we've done everything, but now looking at it physically, there's another kind of feeling that you probably get. The one on the system looks good and all of that, but when you are not looking at it and holding it in your hand, is a different what ball game. And additive manufacturing makes that what very, very easy for us. The second one is what 3D printing takes away the challenge of geometry, having complex or geometry. So I just included a little image on the top, what's left of the screen. You can see what a man is holding on his hand. When you see objects like this, we refer to those kind of objects as what's irregular. They have what organic forms, organic shapes, right? Like more like a tree. You know how the roots of a tree grows, having all those little tiny, what we call it, branches or fins and all of that. So that same form is what you're looking at. So when you have things like that, how do you produce them? Because imagine you are to use a CNC. God knows how, if already you and the operator and all of that will be able to handle the process of trying to cut and remove material to obtain something like what you're seeing on the top left of the screen. You know how the degree of freedom that your machine will need to have to be able to do some of those under works we are seeing inside what that object he's holding on his hand, right? So 3D printing takes away those kind of fears. You understand? It makes it easier for you to get these kind of complex shapes as if nothing even happened, right? As if it's not even a problem from the onset. You understand? So that's one benefit of 3D printing and the additive manufacturing also. The next one is what there are no specialized tooling or essential. We have a low startup what cost, or you even see something like sometimes we even say there's no essentially no startup cost. You understand? We also say, oh, the time it takes to machine or to print and to do post processing. You understand? Are the only things that you could even look at as probably they influence the 3D printing itself. You understand? But if you were to remove all these things, like maybe time of getting the print from the machine out and all of that, you find out that it's cost you little to know to nothing. You understand? When that's with respect to other what's it called, other technologies now, like the subtractive and the formative. You understand? Like for instance, on the injection molding, you have to first of all even have a mold. So where do you even start from preparing a mold? How much does it cost? When you're looking at the costing, that the cost implication of getting a mold, not even the final product. You understand? So all those things now, when compared to 3D printing, 3D printing is way what's better. All right, the next one is a provision for it's makes it possible for you to have high value parts at a reduced cost. You understand? And then there's also something we call lead time. That's the time it takes, the time between you initiating or completing a process. For instance, maybe if you're looking at it from the client's perspective now, you could say, okay, the measure of how long it takes to create and deliver that product or service to the customer. So when you are dealing with 3D printing, you find out that these things are way down. Like they are reduced. That lead time is reduced significantly. You understand? You could see a part on the bottom left now. You can see that's a functional part, a machine, what's it called? A part that will need to withstand pressure and all of that. That's like a valve, like a connection point to another system, probably for flow. You understand? For maybe liquid flow and all of that. So imagine producing something like this and maybe using another manufacturing method, maybe where you have to now remove material, subtract it. You can't compare the cost that it will take you to do that and the cost it will take you to produce that same thing using what additive what manufacturing. So that's why we say what being able to have high value parts at what reduced what cost. So immediately we'll just quickly move on because of our time to what we call the economics of scale. So what I just want us to just quickly take note is that we all know, or even if we did not know, we are getting to know now that the cost is often the governing factor, right, behind maybe a part that will be manufactured. No matter how you speak all the English and trying to convince and do everything you want to do, the truth is at the end of the day, money is involved, and that money is either it is there or it is not there. You understand? It's playing a major role on you being able to say, okay, let us go by this. For instance, you're trying to do rapid, maybe you're trying to do rapid prototyping to just get something out to see if it works. You can't. You have to think twice to say you want to use an injection molding method to produce that out when you have a 3D printing that will just get it done at the snap of your finger. You understand? So yes, cost does affect the method you are adopting. And looking at this scale we have on the screen, we are simply saying, okay, cost per part against number of what parts. So for the first one, the one with the line that has extreme, that has a great curvature, that's the formative manufacturing method. So you could see how the cost per part is at the high end on the left now, right? Follow me on the left part of the screen. The initial setup cost and everything, you can see how it's up there, right? But the beauty of it is that once you're able to have maybe your mode, and now it's just okay, the process of repeating the process of production. So you've already had your mode out. Yes, at a very high cost. And now it's just okay, let's keep on producing maybe 1 million copies. And so you now find out that okay, it's that cost per part now reduces as the number of parts increases. So that's what is happening below. That's on the bottom right of my screen. I believe we can follow what I just explained, right? But when you move to other things like subtractive, you can see how the curve is. And then the one that is of interest, since we are talking additive manufacturing, is the one what's on red, which is the additive manufacturing. So if you see the line, it's just tilting a little bit, telling you that that cost that it will take you to produce, the costing that's per part now, take it to produce maybe, let us say, one part. Even if the price increases to maybe 100, you're still looking about slightly almost the same costing. You can see the line is tilted just a little, almost like someone can almost say it's almost the same thing that it will take you to create maybe one part, and the same thing it will take you to. We're not talking time now. We're not talking about the time now. We're looking at it at what cost per part. So I believe that gives you a little insights to the costing and how it's affects the manufacturing technology, and specifically additive manufacturing technology. So the next one is the DFAM itself, since we are talking about design for additive manufacturing. So what we just saw was just like additive manufacturing in general, right? We said there are many methods. So that was like in general, like just looking at it holistically. But now we are looking at a situation where we are saying, okay, let's tailor the design methods or the tools that we have, right? Whereby the functional performance, another key, let's say maybe product life cycle or considerations such as maybe manufacturing, reliability, and cost can be optimized, but subject to the capabilities of additive manufacturing technology. So that's what we mean by when we say design for additive design for additive manufacturing. So it's not just design, but how are you able to leverage on these things that I just mentioned, maybe the considerations like manufacturing, reliability, cost implication, and how you be able to optimize them subject to the capabilities that additive manufacturing gives you, right? You understand? So that's what we are saying when we say, okay, design for this, design for that, and so on and so forth. So the next thing on our slide is, remember we said the technologies are like SLA, FDM, and so on and so forth. Why the processes are like extrusion, VAT polymerization, and the rest of them. So now we are trying to narrow it down because it's vast. You understand? It's vast. Even the FDM is not something that you can, get everything on one day. You understand? You need to take your time to have that understanding. And even with the theory, it won't end there. Like, you really need to get your hands on it. Like, you need to do the stuff in order for those things that are even mentioned in the theory to make sense, right? So now we are focusing on the FDM, which of course, I also told you the same thing as what FFF, right? So now we can see on the screen, it's typically how it works. You understand? So a spool of filament, right, is passed into what? An extruder, which has something called, a hot end. And, this extruder has like different regions for different purposes. So you could see at the part where there is like some kind of a red line, which is at that point now, you know that that's the nozzle of the extruder, right? It's quite hot. And this filament, which is a material like in a solid form right now, has been melted and passed through, this extruder. Of course, there will be rollers and some mechanical components to help do that, pulling in and stuff like that, because it doesn't just get in. Something has to pull in it, and all those things are also being controlled. But that's not the scope of what we are discussing. So we see the filaments head to the extruder, and then it is passed from the hot end of the extruder or down, right? In a melted form. So solid pass melted, and then now it's gets out. So we could see our the dark line there was saying our bed, right? And then you could see something called support material. So this is basically how it works. When the fluid comes out, right, it gets layered. You could see different layers. Like if you're looking at the line, I see we have first layer, second layer, third layer, fourth layer, and so on. So it gets, and there's a mechanism that is helping to ensure that the filament, which is coming out in a liquid form, is being layered one on each other, and then with some form of pressure to kind of cement them together, right? So the first filament comes in, the second one comes in on it and sticks to it, right? And that it keeps on, when we say building up, right, it just keeps on building up that way to it forms the particular shape that you're looking for, and so on and so forth. So the support material there is just basically telling you that there are cases where we also have to use something, right, as another form of filament now, to serve as some reinforcement, so that the printing will become a success. We'll see that when we move into the actual parameters that influence our FDM. So just take note of this process. I said the solid filament passed through a extruder, melted, and pulled out in a melted form and layered on our bed, right? And then the next set of filaments coming in will be layered on top that one that was layered. So they just keep building, and that's how the object is formed. That is like a very simple way to just look at it. So now one important thing. So we are now heading into something parameters that affect this our technology we are talking about, right? So you could see something called layer height, and then you could see some numbers: 0.05 millimeter, 0.2, 0.3 mm. So those things are usually written in form of what we call microns, right? Right. So if you're saying something like maybe 0.12, what that basically means is 120 microns. If you're saying something like 0.1, what that simply means is 100 microns. So already that could give you the understanding. We are talking microns now, so you should know how very how do we call it now, tiny what we are looking at is. So you could see that the one with the 0.05 has a fine look, right? It looks smooth, it looks well compacted. But on the 0.2, it begins to lose that feature. And on the 0.3 is even more worse, like as if we are stacking some towels, right? So that's basically how it works. So when you are looking at layer heights, we are simply saying that if you have a smaller layer height, you're going to have a smoother surface finish, a finer detail, higher accuracy. For instance, your hole, you want to put a hole, you understand? It's going to come out, if it's maybe you are expecting a 0.5, you're going to have maybe 0.49, maybe 5. I still had to remove a bit of it because even the printer has something called what, a precision and accuracy, which also is probably a story for another day, but it also influences, how your print comes what out, right? So one thing you should know, even if you don't remember anything, is if you're having the smaller layer height, right? Final look, but it will take more time to print, right? If it's the layer heights are bigger, like you see 0.3, the look will be what we call coarse, like, a little bit rough. You could almost physically, depending on the kind of machine now, because different machines have their level of accuracy and finishing, you understand? So some of them, you could almost see the part where the first filament was, and the second filament was cemented, and the third filament, like it's as if you could, with your eyes, separate them. So that's all how the layer height affects your print, right? So we'll just quickly, for the purpose of time, move on to the next slide. So don't, like I said, you should not forget this time. Time is one of the things that we look at when we're talking about layer. It's almost like saying time and layer height have a relationship. In fact, a linear relationship. The tinier the layer height is, the more time it takes. Rather, sorry, an inverse relationship. The more heights, the more time it will take to print, and if the layer heights are more, the shorter time it will take to print. All right, so I'll just quickly move on to the next one. Another parameter that affects this technology is something called shrinkage and warping. So we must have seen this in many other fields of study that we have done. But as it relates to 3D printing, or should I say our FDM now, you understand? So two mechanisms are usually responsible for this, right? Two mechanisms are usually what's responsible for this. So the first one is what, temperature. You could see on my screen, it says a newly deposited layer cools, right? They shrink. When a newly deposited layer cools, they shrink. Now pulling down the underlaying layer upward, resulting in warping. So the first one you're seeing there, you could see like a bed, right? You could see like a bed. And now you could see a material that seems to be in a curve, form going upward. So like I said, two things are responsible. The first one is what's your temperature, what's the differential. That's how we look at it. So if you have elevated temperature printing, this warping usually will occur more in materials that require high temperature printing, like ABS and co. You understand? So the higher you're having those, temperature. So this is how it works. You have the first material that was layered, and we have just discussed that another material will be layered on the first material. So there is going to be a situation. You could already picture that. That means one has cooled to some certain extent, is it not? And then the next one is coming with this very hot temperature to be on the previous one. You understand? So when we say temperature deviation, there's a difference in temperature between the one that was existing and the newly deposited layer. Are we together? So we say with the use of the elevated temperature to produce parts, the extruder, being heated up. For instance, you could have, excuse me, 1 minute, please. All right, sorry about that. So we said we could have a situation where the material was layered, and as one area of the print cools, it contracts, right? Now the contraction for the first one that was layered leads to shrinkage of the build material. So the contraction also pulls on the surrounding areas, creating an internal stress. So it's more like saying, okay, if you look at what the man is holding on his hand, the picture below, you can see something happening where the material seems to be twisted, right, in a certain way. So it's just what we are talking about, the temperature differential. So we have residual stresses. That's when we say residual, that is inbuilt within, and it's as a result of what? Differential in temperature. I don't know if that is well explained, but probably maybe Mr. Felix would add more to that. So I'll just quickly move on to the next one, so I don't waste much time on that. So we have the next one called the support systems. So how does support affect our print? How does support affect the technology itself? Yeah, it does, because support Also, first of all, you're looking at something that could probably add to more printing time, something that could also lead to wastage of materials. And we're also looking at something that could make your printing a success or not. And we're also looking at something that could make your printing have need for post-processing. So all these things I have just mentioned are the baggages that come with support. Not that they are terrible, but they are required. For example, you could see the material on the object on my right, sorry. You could see that it was slanted. So you could also ask yourself, how are we going to, if we are layering the materials, right, from bottom to the top, how are we going to have this material being printed out? Right? Is it going to be suspended on the air? So you could see how the support systems, those ones that look like the tree now, right? You can see how they are helping ensure that the part is in place while the layering is taking place, right? So support systems are, like I said, they add to the print time, they add to the wastage of material. They also make it possible for your material to be, for your print to be a success or not. And they also add or bring in or automatically initiate the need for post-processing. What do I mean by that? After you've printed the object, you see all those things that look like trees, they have to be removed, right? Because they are not the product. So since they are going to be removed, how are you going to remove them? That's where you are now going to go into post-processing proper. How do you think you're going to pull out those things and it does not tarnish the outer surface of what you're looking at on the screen, right? Sometimes you have to just make that compromise, right? Sometimes you have to maybe adopt other means to hide, because there will be tendency of always having the points where the support was to be more coarse than other regions. So it means that wherever you're bringing in the support, the tendency that that place will not look really good. So that's why you're now bringing in post-processing. So what we normally say is, by all means, avoid the support, but if need be, then use it wisely, right? So I think I will just move on to the next one. Layer adhesion. So this is what we are looking at when we said material being dropped. You could see that when a material is being deposited, you could see your filament. So immediately the material is being or in ideal situation, we are thinking of it as the material is being deposited. That's on my left, the left side of my screen now. You can see looking around as if that's how it comes out, but we are saying no. That's the real extrusion profile is what we have on our right. This other one where you see my mouse, right? This is how it actually occurs. So you can see it's oval. So because of this nature, it is actually very tiny. These are microscopic. Remember, we are talking microns now. So like a zoomed form is what you're seeing, right? It's oval in nature. So it has a radius, right? You understand? So now what we are basically saying is, since the deposition and then the adhesion, right? Or since for us to have these materials being layered one on the other, now there is something called adhesion, which is quite important, because if we are not having a great bonding between the first layer and the second layer due to anything, now we are not really looking at the cause. Now we are just saying, if by any reason the material that was first deposited and the one coming in, right? If there is no strong bonding between the two, you're already looking at a failure. The print will, even if it maybe comes out great, it means someone will just probably just try to bend something and everything just goes off. So layer adhesion is very important, as long as this technology is important. Are we together? So you could see the points there where you have we said the real life extrusion profile is oval in nature. So you could see these little things. These are what we refer to as valleys, right? A valley being formed, and this is also telling us that these are the points where a lot of things could go wrong. That's the region where we could have possibilities of failure starting from, right? All right, so I'll quickly, because of our time, I'll quickly just move on, please. I think we still have quite a lot. At least I will just have to cover the additive process. Maybe we'll just leave the generative design for maybe tomorrow or so. So the next thing that's quite important to this technology is print orientation. So there's something I like to remind us of. I know we know this, right? We know this, but we'll probably use it in other settings. So there's something called anisotropy, right? Where you say the tendency of a material, having strength when it's in a particular orientation. So more like you trying to take a saw to cut through a material in the direction of the grains, and you also taking a saw to cut through a material, let's say wood, right, in a direction that is parallel to the grains. We all know that one of them you will have greater resistance trying to cut. If you're trying to cut across it, it's going to be more difficult. But if you're trying to cut in the same direction where the grains, the way the grains are aligned, is what will be quite easy. So that's exactly how it works in this setting, right? So you know that a material will work in a certain way. You look at what we have on our screen here. You could see we said the material is being layered. If you look at this is still being layered from top to from the bottom to the top. If you look at this other one we have on our right, it's still the same thing, layered from bottom to top, but there is a difference, which is how it's going to be used, the orientation. Look at the weight on the member on the left. That's the way the weight is pulling is being applied. And look at the one on the right. Right? So let me ask you, or just look at this. I'm not expecting an answer, but just picture this in your mind. The one on the right, if you're trying to pull apart this material, and we know that the material was joined in this way. Look at how it's joined, right? See how it was layered. Which one do you think would be easy? Would it be easy to pull this apart, or will it be easy to pull this apart? Of course, the answer was very obvious. So it's also very important that whenever you're trying to print, you orient your part such that you don't have your loads directly on the weakest directly on the point where failure will possibly occur immediately, because we all know like what we have on our right hand, if you pull, will likely just fail even without blinking. The material was added this way. So if I pull this way, just like saying, okay, give me back my material. So it will just go up. But if you try that same thing here, you will experience difficulty because of the way the material was layered and the way the forces were pulling, trying to pull. So there will be resistance. That's why we say that the print orientation is quite important, and it affects this technology so much. So lastly, last but not the least, okay, we are looking at infill density and paradanix percentage. They also affect 3D printing, and the reason for this is that you could have a material just like think of maybe like your biscuit, for instance. No matter how thick your biscuit will be that you're eating, you know that when you try to break the stuff, it just gives up immediately. You understand? And one of the reasons is because of when you really take a look at it, you find out that it's almost as if, yes, everything is covered on the top, but inside is as if they are just vacuum spaces. They are not closed material compartments, right? You understand? So when we say 20% infill, for instance, you could see how sparse the materials are. 50%, you could see how sparse, how closely related they are, and then you could see 75%. So how does infill affect our printing or our technology? Yeah, of course, they help you to save material and decrease the build time. That's when you're having low infill density. You understand? But if you're having a higher infill density, the reverse is the case. So why would you want to increase or decrease? For instance, if you're doing maybe just a rapid prototype, you just want to see how that thing comes out, not necessarily whether it's strong or not. You could run your design and print it out of the machine on a 20% infill density. So it's going to be a little bit brittle in nature, even if the material is a strong material. But because it does not have that closely related material, so it's as if you push against it, it's going to quickly sink in. It's going to quickly break. You understand? It's going to quickly deform. That would be the right word. You understand? But when you have more materials, more mass inside, you understand, that is already contributing to strength. So what means that infill density affects strength. So the higher the infill density, the higher the strength of the material. Do you understand? Like not necessarily, you will not be comparing it as per plastic to iron. Now we are saying the same plastic, maybe the same PLA, for instance, print it out, the same geometry on an infill of 20, print that very same PLA with the same dimension and everything on an infill of what maybe 75 or 80, then that's when you really see how that infill affects or makes that material have higher strength or lower strength. I believe we've gotten that part. So like I said, when the material, you're not looking at the functional part or maybe something that will be applied in maybe as a machine member or something like that, you won't, of course, you can't use 20% infill. You start how you're looking at maybe 75% or 80% and so on and so forth. You understand? All right, so I'll just quickly, because of time, it's already 2:39. So I believe we have just maybe 3 or 4 things to look at. So these are the ones that really apply to what we are doing to yesterday and probably some form of today, the fillet. So now, because you know that the material the object you're about to print is going to be on your bed, right? Now it is ideal and it is also very good for you to try to incorporate a chamfer, right, on that part that is going to be on the bed. So on the surface that's going to lie on the bed during the printing is ideal. Now you might ask me, why even put it? Why not reduce it? So this red line that is slanted, just draw it down. Now that would be a problem, because first of all, if you want to pull that out and maybe you did not incorporate a raft or a brim, all I mean by that is there are some things under that will also reinforce and make it stick to the bed, or also help to ensure that the parts is probably properly oriented. So if you have things like that, right, are not included, and then you're placing the material directly on the bed, one of the first things that will happen is, that's what I mean by material, you're placing your what you want to print directly on the bed. What will happen is that when you want to remove it, remember we talked about removing from the print bed, there is likely the tendency that you are going to damage that region where you are making contact to try to remove, because do not forget that this is directly on the bed, and it's during the printing process there's been a lot of ironing from the fillets. Yes, a lot of ironing, a lot of material compartment. If you see when it's printing, you really see how the force it uses to layer one material on the other. So I know that this is probably well sticked to the bed. You understand? So for you to try to remove it, you already was going to damage. That's one of the reasons why we incorporate a chamfer, because now it will be easier for us to be able to pull this material out of this bed, because it's as if we already have an expo right here. Understand? Now, why do we say this is ideal, preferred more than filleting? We will see that in the next slide, or maybe in the next. Okay, yes, in the next slide. But one of the things you need to know is that when you have a structure like this on the bed, and you're looking at the tendency of a failure to occur, the one with that's on my right, the one that is chamfered, will stand the test of time in terms of being able to fail than the one on my right. Are we together? So the one the one on my left, sorry, the one on my right would be able to get printed even without the need of a support system. If you notice, it is about 45 degrees. We'll see it on the next slide. Understand? So there's also like a rule that as long as this does not go beyond that 45 degrees, it will print fine. But when you are using something like a filler, you do not have such control, right? So that's one of the reasons why we prefer using a chamfer over a filler. But you also ask, chamfer is so sharp. If I use chamfer, it might not really give me the kind of look I'm looking for, maybe in terms of aesthetics. So that is why you saw us in the design. We chamfered, then we fillet. So by chamfering, we have stayed within the law, right? By our 45-degree chamfer, we stayed within that law, and then we still apply the fillet to now make sure that these corners, right, are rounded. We have a smooth transition. So even cases of having failure due to stress, all those ones will also be eliminated, because the stress will be well distributed among the member, right? So I'll quickly move to the next slide so you see what I'm talking about. So there's something called overhangs. So a situation where you're printing like what we saw here, there's nothing supporting it, so it's just as if it's suspended, right? So when you have something like that, there are many cases where you have that in your design. So we are basically saying that if your overhang is less than 45 degrees, support is needed. You see that thing we saw before? I told you support, the benefits and the downsides. So by you going below 45 degrees, you're already constraining yourself that this print will fail except I add support. You ask me what is support? It's literally as it is, just to support, to be like a reinforcement for the printing to be layered, because we cannot layer materials on the air, right? We said one material on the other. So at every point in time that the machine is moving, the extruder is carry on its activity, there has to be something, somewhere. It's not doing this on the air. There has to be a material that is now putting another material on top of that material, and it keeps doing that till it's done printing. So we are saying that if it is less than 45 degrees, it will fail because it's as if it's printing on the air. So now you need support. But if you're staying within the law, that is not less than 45 degrees, that means you could still print it fine without the need for a support. That is basically what we're talking about when we, call in our overhangs. So it's left to you, the designer. Are you going to go the path of, so, okay, no problem now, let's just print this in Jare and, add the support? Well, it's left between you and probably your client, because, when you bring in the support, you're automatically inviting post-processing. So except if that is part of the budget, you're good. If it's not part of the budget, then you're on your own. You understand? So we'll move over to the next one, unsupported wall. So you could see this is like a T. So like the alphabet T. So this is basically what happens. See the one below? It prints very fine because it has something like a support, like beams, supporting the extension of that extension that makes it look like a T. But when you remove that thing we are saying, that's the one below, you will have this thing you're seeing on the top where, yes, it's looking nice, but when you now look under, it's messed up. The filament has printed, there was nothing to hold it down. It's began to sag. And so the first one sagged on the second sagged on the third, and they kept on sagging till you have that thing you're looking at there, right? So you will want to try to avoid having things like this. So what you ask me, what about when I can't avoid it? Oh yeah, you use support now. Or probably you have to shut down the extension, because if you look at this T, from this point to this, if you look at this T, from this point to this point has a particular let's say magnitude, maybe 10 mm or 2 mm, you understand? So there are ways we could also print this without support and it will come out fine. Now that is you now adhering towards the rule of, if you have an unsupported wall and you really want to print and you're sure you want to get it out, follow this rule, right? So we'll get to the rule very soon. I think we're already on the rule itself. So this is what we are talking about. So can you say design rules for 3D printing? I believe we'll be able to also send this across to you on the, so you could just look at it in case it's too tiny. So basically, some of the printing technologies are mentioned. The very first one on the top here is what fused deposition modeling, the FDM we talked about. So these are the different things that you can encounter when building. Oh, I have a view that has a supported wall. I have the one that does not have a supported wall, that's unsupported. That one we just saw now, right? I will have a view that has an overhang. Okay, how do I go about it? I want to put an engrave. What's the extent I can go? Oh, there's a bridge. What's the extent I can go? I want to have a hole and I want it to be perfect. What can I do? Right? So you could see all of this, spin, tolerance, and so on and so forth. So let's just look at one, focus on one, which is our FDM, which is what we have been talking about. So for the FDM, I said that if you have a supported wall, right? If you have a supported wall, so we said that the walls that are connected to the rest of the print are at least two sides. That's what we mean by a supported wall. So you could see this wall. Yes, it's a wall, but it is supported on this part and it's also supported on this part, right? So the minimum you can go for it to print well is 0.8 mm. That's what we mean by this value. So this is where you will now, someone asks a question about parameters. I knew most of them, so I just put it in without having to come. But yourself, you might have to go through them and then start maybe put it in your Fusion and stuff like that. So you just come here, okay, parameter. You can name you can even name a parameter supported wall in your Fusion and just put the value. So whenever you're working and you need to call it in, you just call what that value in. Take note, this is what the minimum. This is not like it must be 0.8. This is saying you cannot go below 0.8, but it could be 1, it could be 2, and so on and so forth. Same thing, unsupported wall cannot go beyond this. We talked about the overhang already for the when we talked about filleting and chamfering. So this one we say it cannot go beyond 45. but anything above, we are good. It's going to print very well as if nothing happened. Emboss and engrave. We said that if you're trying to print something, and when we say emboss, just think of this way: you're making a depression. Maybe you write something like your name on let's say on a book, and then you try to push that thing into your book, and then you want it to make like a mark, right? So that one now you're engraving. So if you're doing the reverse, you want it to come out like a protrusion. You're embossing. So whether you're engraving or embossing, there are rules. But it should not be smaller than 2 mm. Understand? And then the width should not be smaller than 0.6. But there are cases, of course, this will be on an advanced level where you could still play around with these values. But as someone who is just still trying to get acquainted with most of them, you probably want to stay beyond that, within that. So the next one, bridges, right? If you have a bridge, so this is, let me just take out, you could see 10 mm. So what we are basically saying at just a moment is that for you to get this T out, you see this T that failed. If this from this point to this point was less than 10 millimeters, it will print. But this person, of course, refused and went ahead to do his own printing and just put, maybe probably this could be like 20. So you could see the failure was taking place. So that's the one thing with the rules are if you do not adopt the rules, you will see the results straight on your print, your final print, right? So we have holes. For the sake of my time, I will just have to move ahead. The chart will be made available to you. You could just sit down and look at it. So you see how I'm going about it. That's exactly how you're going to go. Whatever technology, if maybe binder jetting, you could see the values. So when you see these ones that has crosses, that looks like a rectangle that is crossed, something like this, it means that it is not applicable. So for this technology, unsupported walls is not applicable to it. That's why you could see these words canceling. So I believe we could all read, so we'll be able to understand these terms here. For instance, the hole. If I fuse the FDM, I want to put a hole. I trace down to this point. So what are we basically saying? Right? You could see a diameter 2 mm. So he's saying, please, when you want to put a hole, and you're really sure you want this thing to be a hole on this design, and it's not lost during the printing. Remember, we talked about the material coming out in an oval form. And the truth of it is, after printing, it is going to it's going to have some level of a little bit of increment. It will not be the true size of what you were expecting to have because of the cooling, the heating, and all of those processes, right? And even the layering process itself will cause that little deflection, right? So that is where the accuracy of the machine you're using comes in. You will see some machine that will tell you 0.00 blah 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 plus or minus this. So those accuracies will make it possible that, oh, I want to print 2 mm hole and I will have 1.95. There are some machines you want to print 2 mm hole, you end up with 1.8, right? So you just have to know those things, and then we are saying don't go beyond 2 mm, please, right? So all these values here are don't go beyond. But if you want to go above, you are fine, right? So I've just shown you how to interpret the rules. So you could just go on when the sheet is made available by probably Solo will make it available to you. You could just go to that. So basically, the next two things here is just to simply see where can we use additive manufacturing. So you could see how it's used on the medical field, right? You could see how it's used on the medical field. You could see how it's used on the automotive industry. We could see how it's used maybe for parts replacement and all of that. So this other one where you see a man holding a metal, this is what we wanted to discuss on generative design, but unfortunately we'll not be able to do this today, right? So we'll just probably steal maybe 30 minutes of your time tomorrow to take care of this. Okay, so these are some areas where we can apply additive in even agriculture, fashion. Use it. You could see your pendants, you could see your dresses. You could use it to print something that you want to use for maybe just to test, like some of these, what's it called? I think they call it mannequin in our parts. All right, so you could see this is a 3D printed building, right? In fact, you could even go after this class, just type the first 3D printed house. It's a very interesting documentation, right? Just go around. You even see some houses that are 3D printed with cement, like actual cement, but the technology of 3D printing is being used. So you could just use that to get to know that you are not actually just looking at something that is a lost cause, but something that is very, very interesting and has a very vast area, wide area of application. So I'll just move on to the very last thing, why additive? Why should that even, is it for me? You understand? So you could see some career opportunities, mechanical engineers, software developers, material scientists, technicians, service engineers, 3D designers, technical sales, marketing, account managers, educators, and technical writers. So you see all of this, they all have something that they could, leverage on from additive manufacturing. So this is where I will stop for today. Unfortunately, we can't go beyond this. So over to you, Tolu, and thank you so much for your time.
All right, so thank you very much, Mr. Ofanimi. I really appreciate the explanation, and I know that this is quite a lot for a lot of people and for the first time, but I think there will be questions right before we wrap it up. If you have questions, you can raise your hand or you can ask Mr. Felix to help you mute his mic so you can speak.
Christians. So the essence of what we are doing, like I said, right, just for you to really understand, keep the team, when you're watching the recordings, not just watch it straight. If you watch, you get something, pause, go back and watch, you understand. So there's a lot of, and then sometimes there are things that you also put that context, explain, but you change the new starting to do assignments. You can also use that same challenge to now do a constructive context of the question, not just basic line thing, right? The whole thing and say explain for that. If we have a very like challenge, right? Very good. Think of them and say you can use it. I didn't use it. So at the end, he said, if you do that, you can also use that. If you use the H, you use H. Well, I prefer you to use H ChatGPT, the AI capability, the page, than the direct ability. Why? If that H will give you limits, it will summarize, it will give you the all the other numbers. Because normally H in browser, right? The in browser, the Microsoft, that's right. I also think. So it will give you links where it's summarizing those things. So you can think of those that really normal ChatGPT will not give you the links and the rest of it. I don't know the age I use is beyond just a normal personal, it's a business thing. That's a business, that's personal and that's but me, your personal one, to be able to give you that. Give you those links. So I don't just take what is given you, but also go and do further. Right? You get more explanation, but what I think is about your politics. And read each of them and get more understanding what is saying, not just the summaries. So please, if you have questions, we will keep having it. But I know that most of you are trying to condense what you are learning. Thank you so much. But I know there will be more questions when you guys watch the recording. So the faster you want to, you wouldn't want to have 1 month after that or 2 weeks after that. Somebody will ask you, hey, that what that recording, you have moved that password, move it to the next thing. So the faster you watch the recording, the faster we can be able to relate and attend to some of these things. I know that the way you guys are looking, there's no question. So thank you once again, Ofonime. Thank you also, and hopefully by tomorrow, we'll round up the one of generative design. Hopefully, I hope it will not take more than 1 hour for the generative design since it's just a case study. I hope so. Please. You see how
we'll try to keep it down to maybe 30 minutes or so.
It's not 1 hour, because we have another class for electronics, all those siblings to run the schematics and electronics. So if you see those electronics are important, how you see that and do the schematics and do the PCB and then do the lab. So if you shut down that, you probably will not go to page. Right? So it's not just mechanical, it's not just electronics, it's a combination of so many things together, right? Even manufacturing process, because between your PCB is still manufactured. Right? Okay, thank you guys. And so we do have a wonderful, let's leave you so that we can now go and get something and have a good rest. Thank you so much.
Thank you. Thank you so much.